First thing is to know what they are and how to recognize them. And the way to do that is when you see something that is of the form dy dx plus p of x y is equal to q of x. Now, just to bring you back to the fact that this looks a little more complicated than it is, bring you back to just simple notational matters. dy dx, that's just a derivative. P of x is just stuff with x's in it, function with x's in it, times y is equal to stuff with x's in it. These are not necessarily the same thing, of course, p of x and q of x, they could be, but unlikely. So if you ever see something like that, the goal then is to be able to, again, solve that differential equation for a function. An example of a differential equation that looks like this is xy prime plus y equals 2x. And you might say, that doesn't look the way that does. Well, it does if you divide everything by x. So y prime plus 1 over x times y is equal to 2. Now, of course, you can see derivative, polynomial with x, or function of x, times y is equal to the function of x. Now that happens to be a constant function, but still works. Okay, so the goal is to be able to solve this thing. So the first thing is, I'm just going to leave it as it was given to us. We recognize that it's clearly a first order linear differential equation because I could write it like that, I've already done that. But an interesting observation about this one in particular is that xy prime plus y actually is the same thing as xy prime. You might really have to think about that for a second. So hit pause, take the derivative of xy, take xy prime. Okay, if you did that, you'd see xy prime off to the side is equal to first times derivative of second plus second times derivative of first, which is 1. So you get xy prime plus y. Xy prime plus y. Okay, now what we could do is, to solve this equation, or solve the differential equation, we could simply integrate both sides. So let me integrate, and we will get here xy plus c, right, is equal to x squared plus c. So I'm just going to leave the constant over there. And then if you wanted to actually solve for the function y itself, you could just divide by x everywhere, so you'd get something like that. Right? So that would be this would solve this particular differential equation. So what we're trying to do effectively, once we do some more of these, is we're trying to write it in such a way that it is a product rule. And you can see how this kind of lends itself, this side particularly, kind of lends itself to just manufacturing a product rule. In this particular question, it was relatively simple to do that. It was sort of staring us in the face. We're going to approach that generally, though. So we'll start back with this, although I'll write it a little bit more simple, as y prime plus p of x, y is equal to q of x. Again, remember that the major goal was to utilize the product rule. Okay, now y prime plus p of x, y, that thing we're trying to create a product rule from. So what we're trying to do is come up with something we can multiply by that brings that, that makes that into a product rule. And if you're thinking, dude, why are we multiplying by something all of a sudden? Remember that form that I had this in when it looked like this? Remember, that and that are the same thing. All I did was divide by, that's a 1. All I did was divide by x everywhere. This thing is a first order linear differential equation. Very clear, it's a first order linear differential equation. It turns out though that in this particular question, if we multiply through by x, we get this, and then we get a nice friendly product rule. So I know this one was very contrived, so we're going to approach this abstractly, as I said. So what we're trying to come up with is some multiplier to make this left side ultra nice. So that thing we're going to call the integrating factor. It makes it easy to integrate. And we're going to multiply it by both sides, of course. Okay. What we want is, and this is going to be a non-trivial side note, is this thing right here eventually better be equal to I of x, y prime. Okay? Because if it is, then all of a sudden it got really easy to integrate. So let's just suppose for a second that it is. So let's just say when you multiply all this through, it turns out to be I of x, y prime is equal to I of x, q of x. And I know it's like, wait a second, man, you can't just suppose that. Well, we're going to suppose it, and we'll actually establish the mechanics of it in a second. So now when we integrate both sides of this, this becomes I of x, y. So there was, again, an integral that happened right here is equal to, well, that integral dx, right? And this one's been integrated so it has a constant on it, and I'm going to move the constant over to the right side. So this one gave birth to that constant. Okay, now if that's the case, all we would have to do is divide by I of x. And you would have solved the differential equation because you found the function y. And yeah, it might not be easy to take this integral. Definitely non-trivial there, but abstractly here, as long as we can create, as long as this green box is actually equal to I of x, y prime, then we've got a nice easy solution to our differential equation. Just doing a time check. Okay, so now we really need to think hard about that specific point. What we're going to do is, we're going to take this I of x and we're going to distribute it in here. Once we have that distributed in, it will give rise to a differential equation, and then we'll come up with a specific thing that you can use always with these types, with first order linear differential equations to multiply by. So the end goal is to figure out exactly what that I is that makes this true. Okay, so I'm actually just going to get rid of my original example, and I have that defined over here in a different way. So I'll do all this work in green since it's already kind of lit up for us in green. An extra light might help. So let's take this and multiply it through. We'll get I of x, y prime, plus I of x, p of x, y. Just going to check that real quick. Hey, I'm recording. Can I call you back? Okay, bye. And we claim that that is equal to some I of x, y prime, right? That claim was made right here and utilized right here. Just giving myself some space. Okay, so if that's the case, I of x, y prime, we can take the derivative of that using the product rule, and we get I of x, y prime, that's first times derivative of second, plus second times derivative of first. And on this side, it is what it is. And we can get rid of a couple terms. So we're left with I of x, p of x, y is equal to y I prime of x. And from here, let's see, just making sure I have everything in my notes the same. We can divide our y's out, and we have I of x, p of x is equal to I prime of x. And now actually we've created a separate differential equation. And this might be a little bit boggling to you. Let me just step back and see if we can work. We started from a first order linear differential equation. We said, hey, supposedly maybe I can multiply by something that will create a product rule. If, in fact, it created a product rule, it became very easy to solve. So now we're saying, well, let's suppose that it does. If it does actually create a product rule, we should be able to work with this thing and actually find out what I of x is using differential equations. So from here, what we'll actually do is this thing actually is separable. Okay? So think of it as I of x, p of x is equal to di dx. And Leibniz notation is really nice for this. So now if we bring p of that, we bring the dx over, and we divide the I of x over, we'll have 1 over I of x di. And now we'll integrate both sides. And remember, the goal is to find out what I of x is. And I'm running out of space, and that's not good. So the integral of I of x, you can see, will be natural log. Yeah, I'm really running out of space. So I'm going to leave this as this. And the integral of I of x, where should I put it, is just the natural log of the absolute value of I, or I of x. And I'm going to resume my work right here. I know that's not ideal, but I'm going to resume it over here. If that's the case, then we can exponentiate both sides, and I will equal e to the integral of p of x dx. I know that looks a little bit crazy. And that is also equal, well, plus c, right? And eventually we'll have some constant on there. And that constant you can think of as, think about that constant as e to the something, right? E to some constant value again. So let's just call that, we'll bring it out in front here, e to some constant value. And so we'll just rewrite that as a e to the p of x dx. And if we let a equal 1, then I is equal to e to the integral of p of x dx. Now, what that means for a problem is going back to this. Here's our p of x. In other words, what you have to do is integrate the thing that's being multiplied by y, the function of x that's being multiplied by y, and then exponentiate it. And that value will give you an I that you can substitute in that'll make a nice easy product rule so that you can solve the differential equation. An example is to come, but not in this lesson.